I forgot fucking everything. Shit. How did I forget everything? Holy shit. Hello everyone, by the way. Hello. I hope you can hear me, by the way. Can you guys hear me? Use go away this. Okay, thank you so much. I forgot to update the title. The most important meal of the day. What? Doubly-linked list in Rust. So yeah, notifications are going to be screwed up, but I suppose majority of people will just look at the title when they join the Twitch or something. So maybe they're not going to pay too much attention to notifications. So go away, fucking lazy mate. Hello, Bitstream, Gia, Icorabol, John, Cerimon, Mr. Botka, Zoding. Hello, everyone. Really glad to see you all today. So today we're implementing doubly-linked lists in Rust. So on the previous stream, we implemented hash tables. And today we're going to implement another data structure, another famous data structure in another famous language. So, holy shit, now it's stuck in my head. So, have you guys ever tried to implement a doubly-linked list in Rust? Shigiman, what's up? How are you doing? Hello, Shigiman. Okay, so this is T. Didn't confuse it with anything. This is definitely T. Monica Life, hello. So let's just wait a little bit for the rest of the people to join, and we start implementation, I suppose. So maybe it would make sense to add some sort of a README in here. So it's gonna be README MD. I think it could be similar to the hash table, right? So we can steal some information from there. Okay, doubly-linked list implementation in Rust. So I can just copy paste. Purely for educational and recreational purposes, for real world production, please don't use doubly-linked list. Well, I mean, maybe we want to even just mention linked list from the standard library or something. So let me see. So it's going to be linked list. Okay, so there's several of them apparently. Please use std collections linked list, something like that, or even std collection vec. So vec std, is it in? Oh, it's in std vec. It's 2021 people. Okay. So we're gonna have something like a quick start, and the quick start is gonna be simply cargo run release. Right, and what do we have in here for the references? I'm not sure if I'm gonna use anything for the references today, but the license is gonna be MIT. So git init. Oh, it's already the thing. And now let me do the following stuff. ready, set, go. Rust, do I already have that repo somewhere here? It's going to be Rust Doubly-Linked list. I think I don't have such repo yet. We're going to implement it right now. Right here. Right now. Right here. Right now. In Rust. In Rust. Yeah, let's just keep it like that. So it's going to be public, and let's just create a repo. Okay, project. There we go. I just wanted to copy paste that. Update CMD project. Project. Source code. Source code. And let's update this entire thing. So should be available for everyone. So Yesu. So yeah. So what is a doubly linked list? What is a linked list at all? Who knows what is a linked list? Maybe I'm gonna add actually linked list Wikipedia article as a reference because I might actually use it as the explanation material. Why not? Why not? In computer science, a linked list is a linear collection of data elements whose order is not given by their physical placement in memory, but rather spiritual one. Instead, each element points to the next. It is a data structure consisting of a collection of nodes which together represent a sequence. See? So dynamic lists redirect here. So there's some problems with this article. I'm not sure if I want to refer to this article, but yeah, I guess I don't really have that much choice. So I'm gonna just do something like that. References, right? And thank you so much, Google. Very cool. Okay. Add Wikipedia link to add a link to Wikipedia article about linked lists, because Wikipedia is a very reliable source of information. Okay, and let's push that right into the repo. You can find the source code of this thing in here. If you want to follow along at home, you can find everything there. So this is a single linked list. So we have a node, it contains a value, and it contains a pointer to the next element. And then that element, basically the same element as the previous one, it contains a value and pointer to the next one until we point to null or like some last element. Linked to linked list article link. Yes, that's what we did. But this is a singly linked list. It's only singly linked list. So a singly linked list could be represented like this, right? So you have a value and you have a pointer to the next node. So box in Rust is a pointer. It's usually a pointer in a dynamic memory. We can even check it out somewhere here. Dead code, yeah, sorry. It is what it is and it isn't what it isn't. Sometimes you have to dead code your code. So, a pointer type for heap allocations. That's what it is. Pointer type for heap allocations. But what's interesting about box is that it cannot be nulled. It's a pointer that can't be nulled. So to make it nullable, we have to wrap it into option. So you have a T wrapped in a knot, wrapped in a box, meaning that that node is located on a heap, and also wrapped in an option, indicating that that pointer can be nulled to indicate that we're pointing to the end, to the end of the linked list. Right. So a doubly linked list would look something like this. So basically, each node keeps track not only of the next element, not next node, but also the previous one. So in that case, in Rust, it will be represented like this. All right. So I'm gonna go to the kitchen, quickly turn on the kettle, and I'm gonna be back, and we're gonna try to implement this entire thing. Yeah. I guess I want to implement something that is called deck. Essentially a data structure where you can push back and push front in all of one. Right, so, and in that case, deck is going to store the elements of T. Right, and I suppose we're going to keep track of both of the ends of the linked list. So we're going to point to the first element and to the last element. So that way we'll be able to push from that way we'll be able to push front and push back. Thank you so much, everyone. Yep. Kok yasa. Yep. Thank you so much. So that means we need to keep track of the beginning, right? So, and it's also like an optional thing in here. Right? It's also an optional thing, and the end. And by default, both of these things are going to be pointing to none, right? So initially you didn't have anything, and then you're going to have something once you push something, push front and push back. So let's do implementation T. And one of the things we're going to have, first of all, new, right, which will return a new thing in here, and this one is to do, and we need to have two operations in here, push front, so that way you will be able to push a value. So of course this thing has to take a self, a mutable self, and by the way this one has to return self. So we push in a value front, right, and pushing the value back. So this should be enough for us operation to implement for now. Later we can always add more. Let's see if this entire shit compiles. And it compiles. First try. Got cooler. How about that? I'm transitioning as well. Interesting. Language replacement therapy. So, how are we gonna create this entire shite? How are we gonna create this entire shite? Self. Let's just assign both of these things to begin and end. There we go. So this is how we're gonna create a new deck. Thinking maybe I also need to, let's create it somewhere here. So it's gonna be something like access, right? And it's gonna be deck. And what we're gonna put in there? Let's put some strings maybe. I think strings would be actually great. So, and then we want to actually do something like push front. So we're gonna push A to string. So this is going to push A to string, then push back B, and push front yet again something like C. So I'm thinking, how are we going to debug all of that? That's a very interesting question. How are we going to debug all of that? So maybe I need to implement like, to be fair, I just need to probably implement something like this. Actually somewhere here, debug, but I want this thing to actually print the sequence. So that means I will have to implement my own debug interface or something like that. So let me see. So this one has to be, so how complicated debug actually? How complicated it is? I mean, in terms of as an interface, is it too complicated to implement? Is it too? I don't see declaration. Here it is. So you only need to do FMT and you accept formatter. And formatter is I don't want to deal with that. I really don't want to deal with that. Seriously. Let's have a function that basically just prints this entire thing for us. So this is going to be fn dump debug, or maybe debug dump. It's going to be accepting self as a reference, and it's going to be just iterating until the end, until the null. So how are we going to be doing all that? So maybe I'm going to actually start as an iterator. I'm going to take self begin, and while iter, is there something like while let in Rust? I guessed it. There is such thing as while let. It's got letting. You know how I guessed there's while let? Because if is a special case of while. Essentially, if is a while that makes at most one iteration. Without else. If you basically remove else, but semantically you can think about if as the while. Another cup of chocolate. Naizu. More chocolate. For the choco god. What's up, Heroes and Plus, by the way? Hello. Welcome to our epic Rust Club. Oh shit. What's up? Okay, again. So while let some node, we're going to be just printing this entire thing like that, right? So, and I don't remember, I think node, I have to dereference the node, but maybe I don't have to dereference the node. but to print it, I probably will have to dereference it. Yeah. And then I'm going to do the following thing. Iter is going to be equal to node next, right? It's going to be equal to node next, and that's pretty much it. So maybe I also need to space it out a little bit, and then also print a new line here, just in case. So yeah, this is a debug dump. This is a debug dump. Let's see if this entire shit is going to compile. How about that? How about that? And does it compile? It does not compile. Okay. Yeah, so we need to remove that. We definitely need to remove that. Okay, and this thing is not printable. Let's actually make it debug printable. Debug printable, and yeah. So I suppose node. Actually, we need to get the node value, right? We don't need to print the node itself, we need to take the node value. So, and it also means that t has to be debuggable, right? So this is where we're gonna do where t is debug. Frank GB, I hope I pronounce your nickname correctly. Thank you so much for 100 bits. Thank you, thank you, thank you. I really appreciate the support. Thank you, thank you, thank you. Cheers, by the way. Okay, so does it compile? Debug is not a trait. It's probably because debug is located somewhere in FMT. I keep forgetting where it is located usually. I think it's std fmt debug. Here you go. Std fmt debug. Right. So is it gonna work? Is it gonna work now? I think it worked. So, oh, okay. So this thing cannot move out of self begin, which is behind a shared reference. Move occurs because begin has type option, which does not implement copy trait. Can I just take it by a reference then? So, and this is where we're starting to have interesting problems. Can I just have it as a reference? And then expected reference but found option. Okay, can I do something like this then? And it worked. Okay, I actually didn't expect to manage to do that, but it actually worked. Okay. So in here, this is a reference to option of box of node of t. A reference to an option of box of node of t. All right, so if we try to run this entire thing right now, right? If we try to run this entire thing right now, it's not going to work because some of the things are not implemented yet, right? So specifically, we never implemented push front, right? We never implemented push front. So let's try to do that. Where is my? Here it is. Here it fucking is. So initially begin and end actually point to nothing, right? So the usual case in majority of the situations is going to be something like this. So this is going to be begin, right? This is going to be begin. Then you're going to have a bunch of things in here. And of course, since it's a doubly linked list, you're going to be pointing in the opposite direction as well. And this is going to be end. So usually if you want to implement pop front, you would just take begin, allocate a new node in here, point that node in here, and then that one to here, and then just move begin to here. And of course, like this thing to null, right? Something like that. But at the beginning, when the entire list is empty, what you're gonna have is both of these things, begin and end, pointing to null, pointing to none rather, because we're using option as a nullable reference. So we need to handle this kind of situation, I suppose. All right, let's handle this kind of situation. So that situation occurs when so this is a front, right. So here we have something in the list, but otherwise we don't have anything in the list. So when we don't have anything in the list, what we need to do? We need to create a new node, right? So let's put it like this. Yeah, I need a mutable node, new node, and it's gonna be box new, and I need a way to create a new node. I suppose I need some sort of a constructor which will accept a value, right? Which will accept a value and move it into this thing. So if I remember correctly, I don't remember how to use boxes. We'll see. So this is going to be box, and it should have a method. It's going to be fn new, and it just accepts a value and moves it inside of itself. Right, that's what it's doing. It just moves it inside of itself. Okay, for the node, let's just create implementation. It's going to be T for node T. All right, I'm going to have something like new value like this. And this thing is going to return self. Right, this thing is going to return self. Value is going to be moved into itself. Next is going to be none, and previous is going to be none. Okay. All right. What else do we have in here? So semicolon. Missing trait in trait implementation. Okay, I'm sorry. So there should be no for in here. I forgot the syntax a little bit of the of this thing. So here we have a semicolon, and what else do we have? Begin. You might mean field. Yeah. So this is a self begin. So let's put it like this. It's a self begin. Oh my God, Emacs, come on, Emacs, I believe in you. Now, let me see. Consider borrowing here. Okay, so essentially here we're moving this entire thing, but we have to borrow it. Okay, I think that makes sense. All right, so help, this is intentional, prefix it with, well, it's not particularly intentional, so I want to take a look at the error. Oh, okay, it worked. Okay, it worked. All right, so this is a new node. And since we know that begin is empty, the entire list is empty. But there might be a situation when end is actually not empty. It should not happen, right? Since there's only one way to construct deck, and you know, it sets both of them to none. But it might happen because of you know, somebody introducing a bug in the implementation. So we need to check that invariant. So if begin is none, the end should be also none. So we have to do something like assert self and is none. We have to ensure if it is not known in this specific constant, in this specific context, that means the list got corrupted for some reason. Maybe somebody introduced some implementation in modular methods and screwed something up. We want to make sure that, yeah, this is our expectations. Now, so this is the box and stuff like that. And what I want to do, I want to set self begin to some new node, right? And I also want to be able to point at some new node. There we go. So I wonder if it's gonna work, because we're borrowing this thing. Maybe we have to borrow it as a mutable thing. We'll see. So let's see what our compiler will tell us. Move occurs because new mode has type box, which does not implement copy. Yeah, so essentially we need to make this entire thing actually point to this. Yeah, I think box cannot point to the same same thing from two places. I think box is like a unique pointer. Deep Singularity, what's up? Hello, hello, how are you doing? So, what if we use reference counters? Maybe we should try to use reference counters instead of boxes. So should we use atomic or single-threaded reference counters for a singly linked list, or doubly linked list? Actually, we're doing doubly linked list. Single-threaded reference counting pointer stands for reference counted. Okay, so it has pretty much the same interface as box, right? So it has the same interface as box. Let's see if we can do something about it. So RC, right? So we need to do stdrc. So I think we don't need boxed anymore. So it's going to be RC, RC. So expected struct box. Okay, so oh yeah, there is another places where we forgot to replace it. So it's going to be RC in here. Another one. Okay. Expected struct RC. Oh yeah, okay. So this one has to be RC, right? So this is RC, and alrighty. Move occurs, we're actually moving it in there. Okay, can I just clone this entire thing? So I'm actually cloning reference counter, incremented the counter, and then I'm cloning it yet again. Right, I'm cloning it yet again. I didn't think it needs to be mutable, but anyway, I think the compiler will tell me. And once we're out of the scope, this reference counter will be destroyed, but the object will still survive because there is at least 2 reference counters here, right? There's at least 2 reference counters in here. Alright, so everything seems to be working so far. So let's try to build this entire thing. Object will survive, yes. So, but we only implemented like one case, right? We need to implement the second case when begin has something. So in that case, we need to actually create this entire thing one more time. So unused parameter node. Yeah, I want to go through the warnings just to see if it has anything to tell me. It's intentional, yeah. Just I want to fix all the warnings and just see if I didn't miss anything. Is never read. Is never read. Never read. Object dump has never been used. Well, I mean, yeah. Debug dump, and we can just do it like that. And that's pretty much the only. Okay, so this is pretty much the only problems that we have in here, right? That's pretty much the only problems that we have in here. Alright, so I need to repeat this thing in here. And maybe, since it occurs in both of the branches, I can do that somewhere here, right? So we can first create this entire thing and put it into the dynamic memory and only then go here. Okay, so next. So this is a node, right? What I need to do, well, this thing has to be mutable, right? This thing has to be mutable. New node, next has to point, next has to point to the node itself, right? To the node itself. Node itself is actually a reference counter, so we have to do something like node clone. Right, so this is what we have in here now. This is what we have in here. Node previous should point into new node clone. All right. and then node should become new node, I suppose. It may not work actually. Let's see what the compiler will tell us. Let's see what the compiler will tell us. So there's option. Something is wrong with the Emacs right now. So node clone, that means it has to be sum. Yeah, we have to wrap it into sum. Yesu, and kawaii fucking desu. So maybe also sum. Okay. Expected mutable found RC. So maybe it has to be something like this. I have to dereference it first. Okay, so there's that. Okay. Deref mutable. Trait deref mute is required to modify through a dereference, but it's not implemented. So do I have to do something like this? Do I have to just dereference it first and only then clone it? Okay, so here is another one. Emacs, could you please tell me? Okay, so maybe this is what I have to do in here. I have to put references in here. So this is a warning. And for some reason Emacs is not particularly convenient in here. Still doesn't really work. Does anyone know why? So deref mute. Let's actually read about deref mute. Hello everyone. So used for mutable dereferencing. Okay, operations like in addition to being used for explicit dereferencing operation with an array operator in mutable context, blah 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 blah. Okay. I don't know why it doesn't work. Deref mute is required for modifying. So RC deref mute. Can you borrow RC as mutable? You cannot borrow a reference counterpart as mutable. This is because one of the guarantees it provides is only possible if structure is read-only. You can, however, get around it, but it will require some signature changes. Oh. You need more and more layers. You need more and more layers. To be fair, the entire idea of implementing... I don't know much about Rust, but as far as I know, the entire idea of implementing doubly-linked list like this is kind of like a dead end. You're either not going to be able to do that, or you're going to end up with a very slow implementation. So as far as I know, but I don't know Rust that much to actually, confirm or deny. So apparently implementing doubly-linked list in Rust is a like unsolved computer science problem. Well, I mean, it's kind of solved, but it's just like extremely painful. And the main argument why is because you shouldn't use them in 2021 anyway. That's literally usually the argument of Rust people of why it is so difficult to implement doubly-linked list in Rust is because you shouldn't use them in 2021. I don't know how that supports anything, but that's the argument usually. One of the ways I want you to try to implement doubly-linked list today. So I actually went this thing intentionally. I want you to push it as far as I could until I hit something that I cannot resolve, and I hit something I cannot resolve, and to be fair, I don't really want to bother resolving that. So what I want you to try to do today, I want you to implement doubly-linked list based on indices, right? Because indices actually bypass a lot of limitations that borrow checker put in place. So indices in the vectors and in the arrays in Rust are usually used to basically bypass borrow checker. So that's sort of like a hack. Yeah, so this is what I want you to try to do today. And to do that, I want you to implement like a custom allocator for the nodes, custom allocator for the nodes, and then implement a doubly linked list around that allocator. So yeah, that's gonna be the idea. I don't know, maybe there is a way to actually resolve this problem. It's just like I'm too lazy to actually go there, and apparently you need another layer of abstraction there, and who knows how many layers of abstractions you need to go there. And the fact that we have to use reference counting for doubly linked lists is already very sus. So I'm definitely going to end up with a slower implementation than I could have if I just implemented it in C without reference counting, right? So you know what I'm talking about? But of course, I need to mention that the C implementation would be extremely unsafe, and it would be very unethical of me to even try to use such an unsafe language. Yes, of course. But I mean, besides that, right. So we don't want to be unethical in 2021, right? So let's actually ditch this entire idea. So I'm going to completely remove this entire shit. I could have tried to push it and maybe come up with something, but to be fair, I just don't want to. So I just really don't want to. So we're going to implement a custom allocator based on a vector. So let's introduce a structure called memory, and let's say that memory can also only store this kind of values. All right. So what we're gonna call it? I think we're gonna call it a buffer, right? So we're gonna call it a buffer. It's gonna be vector of t. All right, and let's actually make an implementation t. Memory t, and we're gonna have a constructor u, and it's gonna just return self, right? It's gonna return just self, and it's gonna be slef. All right, and it's gonna be buffer vec t. So the reason I was pushing like as far as possible is because I was hoping that maybe one of the professional Rust developers will actually start helping me and backseating me into like a right and proper implementation. But once I hit that Giraffe mute wall, nobody was saying a single thing. It's kind of interesting. Like everyone was absolutely silent. Like and explicitly ask how do I solve that? Nobody said a thing. Once I disclose that I'm doing that intentionally, let's do it a different way, everyone is just like starting to say that, their opinion about this kind of thing. Like everyone is suddenly talking. Where have you guys been when I had a problem with Giraffe mute, and why didn't you guys help me? Professional Rust developers, just saying. It's just kind of funny, I think. Okay. Where have you guys been? Like all of a sudden, once the problem becomes simpler, everyone understands it, and bike shedding begins. I'm sorry. So, so what are we gonna have in here? So we allocated this entire thing, and let's just create a memory. So this is gonna be something like this: memory. What we're gonna allocate in there? We can allocate like i32s, right? i32s. So alloc, right? So are we gonna provide a value for this thing? Are we gonna provide a value for this? Maybe something like this, value t. And this entire thing is going to return actually an index in that array, right? It's going to return an index in that array. So this is going to be to do. All right. So, but here is the thing. Buffer, I think buffer is supposed to be like unavailable for like outside of the memory. So also I forgot self. Mute self, and there we go. So maybe we're going to implement a method called something like Giraffe, right? Something like Giraffe, which is going to accept immutable self and an index, which is usize, right? And it's going to return you this thing. It's going to return you a reference to that element that you allocated for yourself. And we also need to have something like Giraffe mute, I suppose, right? A mutable version. And this one has to be mutable, of course. Okay. So, what we're gonna have in here, so let's try to allocate something like P. Alright, and I'm gonna do memory, allocate, and I'm gonna allocate 69 in there, right, and we have our index. Let's put an index in here. And another thing I want to do, I want to print a len memory Giraffe, and it's going to be index. All right, so all right. Okay, something like this. And let's try to run this entire stuff. Yeah, okay, so we have a couple of things that are not implemented yet, and we also have a couple of things that are not needed anymore. We don't need any of this stuff. And we probably don't need a debug thing as well. So this is going to be something like this. And yes. So you just re-implement row pointers. What are you talking about? Row pointers are unsafe. Do you see a single unsafe word in here? You're insulting me. Excuse me. Are you accusing me of using unsafe code? I'm deeply insulted. What the fuck? Okay, so I'm sorry. So we're gonna do this entire thing, and let me see. So when we're allocating something, right, what we're gonna be doing, right, we're gonna be actually taking a self buffer and push the value in there, right, and I suppose the index has to be something like self buffer len -1, right? So this is going to be the allocation. So the next thing we do when we dereference this entire thing, we just take self buffer index and we just return it by a reference. So this is basically what we're doing, and I suppose we can do the same thing for the mutable one. Same for the mutable one. And it works. So as you can see, we implemented a very simple allocator which is very specialized allocator. It can only allocate certain types of objects. We allocated an object inside of that allocator, and we actually get an access to that object in that specific place of memory. So this is a very simple custom allocator. And it's based on indices, but indices are not type safe. They're not particular type safe, they're just numbers. So how do we know that this particular index actually refers to the type T? Right, the cool thing about references and even row pointers, God forbid row pointers, very unsafe feature, God forbid row pointers, they have at least one important thing. They have a type attached to them, which actually allows the type system to check if you're referring to what you intend to refer. Unfortunately, indices, while being relative pointers based on the particular base, which in our case is going to be vector, they don't carry this kind of information, so type system may not help us in this particular situation. But we can come up with something. Let's introduce a type that we're going to call a pointer. And this type is going to wrap the index. It's going to wrap the index. As far as I know, this is not going to compile. because in Rust you're supposed to use this type parameter, but the idea is going to be the following. So we're going to have implementation type pointer t, right? It's going to type pointer t, and we're going to have something like from index, right? So we're going to accept an index, and you're going to return self. I'm going to return self, and self is going to be just index. There we go. Index. Cool. Now, when we are allocating this entire thing, we're not going to return use size. No. We're going to return pointer to t. And then we're going to actually construct something like t new, from index, right? From index. There we go. So we have additional layer of type safety around our index. Isn't that amazing? So it's not just a raw index. You have type associated with that index. So you won't be able to take an index that points to string and dereference it to get an integer. You can't do that anymore. The compiler will actually type check that. So it's absolutely amazing. Anyways, so here when you dereference something, you actually accept a pointer, pointer t. So, and I think maybe we need to make pointer copyable. So it's going to be derive copy. First we have to derive clone and then copy, right? So it's going to be clone and copy. And here, what we're using, oh, we have a raid from Provet. Hello, everyone. Why did you raid me? Didn't you see the title of the stream? Are you guys sure it's gonna be interesting for you? We're implementing doubly-linked list in Rust. But since implementing doubly-linked list in Rust is a huge pain in the ass, we're making our own allocator. Isn't that cool? I think it's pretty cool. We're sure that doubly-linked list in Rust should be a fun project. Yes, it is fucking fun. If you try to start implementing doubly-linked list in a very naive way in Rust, you'll quickly realize that you need reference counters, unsafe cells, and shit ton of other layers just to satisfy the borrow checker and the type system. It's like, it doesn't look that bad at first, but as you go deeper and deeper, you realize how fucking deep that rabbit hole is. It's just fucking insane. And then you realize, okay, I have to do something. Like, the easiest way would be to just use unsafe features, but another one is to actually make the linked list based on indices inside of a vector. So, and for that, we're implementing our own memory allocator, which is based on indices. I don't know if it is possible. There's like a whole article. So if you Google Rust doubly-linked, I think it's something like too many linked lists. Yeah, so this is like a whole discussion. Yeah, I really recommend actually reading this entire thing. So it's not fully finished for some reason. Maybe the author kind of abandoned it, but they went through different strategies and different ideas of implementing singly linked lists and doubly linked lists. And this is like a whole book or something. Imagine your type system being so goddamn annoying that you can make a whole book out of implementing a linked list. Imagine that. Just let that sink in. It's not really a book, I mean, but it's like a mini book, right? It's not like a full size book, but I mean, you see what I mean. Anyway, so Book of Sorrow, yeah. Classic Rust. Anyways, so what we decided to do, we decided to implement our own memory allocator, which is basically a vector, right? And when you allocate a new object, we just push that value into the vector and we return index as a pointer. Right, so a pointer is essentially just a structure that wraps an index and it hides away the index from you, so it acts like a pointer. So yeah, now we have a custom memory and we have a custom pointer, so we're basically emulating our own memory. So we are rejecting memory model of Rust and returning back to our own memory without any unsafe, by the way. There is no single unsafe in here. All right, so let's continue. So you practically, what are you talking about? There is not a single unsafe. How is this? This is as safe as it can get. There is not a single unsafe keyword in this code so far. But I don't plan to add any. So I think it should be possible to do that without unsafe keyword. So anyways, yeah. So this is how we do allocation, and we need to do the allocation. So it's going to be like this, and this one is going to be a pointer. It's going to be pointer t. This one is going to be a pointer index. There we go. Oh yeah, this is a very interesting thing. So if you have a generic parameter in a structure, you are legally obligated in 69 states of United States of America to use that generic parameter, and if you don't, you will go to jail. To actually bypass that, you have to use something called phantom data. So phantom data, where is it? Let's put it somewhere here. Phantom data. So basically, it allows you just tell IRS that you know, you use it and you just write it off. You just write off that specific generic parameter quite safely. All right, so let me now put this thing in here. So it's going to use phantom data, and how do you usually call it? Yeah, usually called phantom. Phantom, and it's going to be phantom data, and we just say that this thing should act like a reference, right? This thing should act like a reference. So it should act like it owns the reference to this thing, but maybe it should act like it owns the data. Let's actually say that it owns the data. Cell missing phantom. Okay, so the thing about phantom, as far as I know, is that you can just do default, I'm pretty sure, right? So it's gonna work. And it's working. Would you look at that? So now you have a pointer, right? It's actually called PTR, and you then dereference this entire thing, and yeah, you just printed it. And as far as I know, you can also do something like memory deref mutable. You provide the pointer, and I guess I can just do something like this, then try to dereference yet again and see if the value got modified. And there we go. So we allocated a single slot in our memory allocator, and then we updated that slot, and here is the new value. So there you go. So we can allocate an object and get a pointer to it, and then dereference it as immutable and then as mutable. So we have our own memory allocator that we can use. Isn't that amazing? I think it's goddamn amazing. So let's just use this memory allocator for implementing a linked list. So we need to have a node, right? So it's going to be a node that contains t, right? So it's going to be something like value. Then we're going to have next, which is a pointer to t. And since our pointer also cannot be nullable, we have to wrap it in option. So this is one of the things we'll have to do. And the same thing is going to be previous. This time we don't have to... Well, yeah, so essentially we replaced box and reference counters with our own pointer. So that's one of the things we can do. All right, so now let's implement deck. Let's implement deck. So deck is going to point to the begin and the end, and it's going to be option ptrt, and yes, exactly. So let's implement deac. And it's going to be fn u. Okay, what kind of operations did we have? Push front, and pushback. Right, that's the thing we need in here. Not the things we deserve, but the things we need. Push is going to accept immutable self. Oh shit. Immutable self, the value that you want to push in there. And what's interesting is that it also, unfortunately, have to accept the pointer to the memory, right? And since we're going to be allocating into the memory, we have to accept the pointer to the memory by mutable pointer, and we expect to allocate nodes in that memory. That's right. So this is going to be basically our signature. To use linked list, you will first have to allocate a memory, your allocator, and then pass that allocator to deck so it can allocate memory in that allocate objects in that memory and reference them and do something with them. So yeah, that's basically what we need in here. So it's going to be to do. I suppose pushback is going to have a similar signature as well. A similar signature as well. All right, so something like this. And all right, looks cool. Let's try to compile this entire thing, and it compiled without any problems. Would you look at that? All right, so yet again, front. You can have two situations, right? Basically, when the deck is empty and when the deck is not. So that's basically the situations you can have. In any case, we need to probably allocate a new node first, right? So it's going to be something like new node, and we take the memory, right? We take the memory and we allocate a new object. And we actually move value into that object, right? So memory alloc. So, and we get the pointer. We get the pointer to the new node. What's interesting is that we don't even have to mark new node pointer as mutable, which is actually kind of interesting, right? Because it just doesn't matter. So you can use pointer as mutable and as immutable however you want, and we don't use a single unsafe keyword. We bypassed the entire borrow checker, the entire type system, without using any unsafe keywords. This is amazing, isn't it? And this code is still safe. As far as a Rust compiler concerned, this code is still safe, right? So there's not a single unsafe keyword, so it's totally fine. So it's within the rules of the game. Okay. Now, so what we need to do here, we need to take self begin, and I think we need to do something like some node. Right, so this one is going to be something like this. This is going to be to do. It's like transmuting reference. No, transmuting actually requires unsafe keyword. Right, transmute. Yeah, so if you take a look at memory transmute, you see it's not only unsafe function, I think it says that it's incredibly unsafe function. Right. It's not just unsafe, it's incredibly unsafe. We don't have to use any unsafe keywords in here. Our code is absolutely safe, if I understand correctly. So, yeah. Anyways, let's continue. Our code is absolutely safe. So here we have to assert this entire thing. And again, if begin is none, we have to also confirm that end is also none. Otherwise, we did an oopsie-doopsie. So after that, what we do, we take self and we say begin is equal to new node and end is equal to new node. That's it. as far as I know, that is pretty much it, and that will just compile. Hopefully it doesn't compile. Okay. Expected. Oh yeah, you have to. Okay, so we have to wrap this entire shit into a node. Yeah. So, but I didn't think we have a constructor for the node. So it's going to be something like impl t node t, and let's do something like fn u. And it's going to be a value, right, that you're moving inside of this entire thing, right? It's going to be self, this is going to be value, right, and then in case of the next it's going to be none, and instead of in case of previous it's going to be also none. I can't tell if it's actually safe or not. It's just a joke about, of course it is fucking safe. If it was unsafe, Rust creators would actually forbid this feature, and or at least put it under unsafe. They didn't. That means it's totally safe. So there is absolutely safe way to trick the borrow checker. So it's within the rules. So Rust developers, it's as Rust developers intended. Zockenheimer, what's up? How are you doing? Hello, hello. Okay, so I'm not violating. This is still a safe Rust. It's not just Rust. This is safe Rust. Absolutely safe Rust. Okay, so this one has to be sum, and this one has to be sum as well. So type parameter. Oh yeah. I completely forgot. Yeah, so it was actually kind of sus that there was not enough layers in here. So yeah. All right. So self begin. Consider borrowing. Okay, so I should be able to borrow it like that. And let's take a look at the rest of this stuff. For some reason, Emacs is really being annoying in here. I'm not sure why. Move occurs because it has a type which. Well, I mean, pointer. I think it should implement copy. It does implement copy, doesn't it? So what does it say? Move occurs because node has type which does not implement copy, but it does implement copy. You see? Here it is. Here's the copy. Well, I mean, I can try to explicitly say that I'm cloning it. Okay, I can explicitly say that I'm cloning this entire thing. Is it going to be happy now? Oh, node. Oh my God. Node has to set. All right, I see. Node has to satisfy. Can I just say that it's a reference? Maybe in that case it doesn't have to satisfy, and then it has to have a lifetime. Yeah. But if node has to be copyable, right? Node has to be copyable. That means the T also has to be copyable. All right. So maybe it's not as easy as I thought. It's still very interesting. All right, so let's just make it clonable then. Wonder how far I'll be able to go. Derive clone, right? So this is going to be a node, and yeah. think I'm getting tired. I think I'm getting tired. So let's make a cup of tea, I suppose. Let's quickly make a cup of tea. Let's quickly make a cup of tea. We'll see. So, do you guys have any questions maybe about what we're doing right now? Well, it's actually safe, but actually it's absolutely safe. You see, the compiler, the Rust compiler already doesn't allow me to do stupid shit. So that means it's safe to some extent. Right. So we'll see. Maybe it's actually safe. Who knows? Okay, do you guys have any questions? I'm making a small break and making a cup of tea. So okay, very well then. Okay, no questions so far. All right, very well then. I'm gonna go to the kitchen and just turn on the kettle, and I'm gonna be back pretty soon. I just need to warm up some water for my tea. Making a cup of tea. MKT. MKT. All right. You know what's interesting is that if we won't be able to make it work, we can always strip off PTR, right? We can just strip off PTR and pass around U sizes, and it's, yeah, it's just not gonna. So we can bypass the Rust compiler even further. But I don't really want to bypass it too much. It would be kind of cool to at least have some sort of type checking, but still be able to bypass it. See what I mean? See what I mean? But since we slapped like a type on it, we may not be able to easily bypass it, because now the pointer sort of becomes part of the Rust system, and that's what actually makes it interesting. So maybe we're about to learn something cool. All right, so new node. So here's a new node. We allocate this thing. It becomes a value, so it becomes a pointer, right? Oh, I see. Node has to point to itself, of course. Okay, I think, but I'm not sure if it's gonna solve anything. I'm not sure if it's gonna solve anything. Look at that. Look at that. Isn't that beautiful? I think it's got that fucking beautiful. Yes, yes, yes. This is so sad. I bought 3 pairs today, right before the stream. And I already ate them right before the stream. And I want more. See, how do you pronounce it in English? Pa or P? Well, okay. Let's listen to different pronunciations because I'm not a native English speaker, so I might actually be very pepeg about how to pronounce. So let me see.
Pa.
Pa. You pronounce them same. Okay, I see. And UK pronunciation is like pa. And if I take a look, okay, so this is a transcription, and pa. It's literally the same transcription.
Pa.
I'm pretty sure they reused the same sample. So, all right. Very well then. Pear, like beer. Somebody either fucked up or tried to debate me. So alright, so let's try to compile this entire thing. And what do we have in here? Clone not found for this thing. Maybe you also have to mark T as clonable. Pair programming. Okay. Oh shit. Oh fuck. Shit. Fuck. Damn. I wonder why the fuck it has to be. Well, I mean, it's because of that. Because we're cloning this entire thing. By the way, I wonder how RC actually implements that. How RC actually implements that. How do they bypass that? So RC, I'm pretty sure, also uses Phantom, but it might be using Phantom in a slightly different way than we do. So let me see what it's capable of. So T is sized for some reason, but it's not that important. RC box. And RC box is this thing. And it's actually storing this value in there. Strong Vic. Alright. It's doing the same thing pretty much. It's pretty much doing the same thing. Yeah, and it's also using like non-null pointers and whatnot. I don't even know what is non-null, but it's yet another one of those types, which is, okay, non-nullable pointer. I see. Yeah, they're just using non-nullable pointers. Okay. But what's interesting is that if you have RC, you don't really have to make your thing clonable. It might have something to do with size, but I'm not sure how this sized marker actually works. Type with a constant size no one at compile time. All times parameters have an explicit bound sized. This special type sized can be used to remove this bound if it's not appropriate. Okay, so it does not have an implicit size bound. Okay. Ah, I see. I see. So basically it allows to use traits in here, the size of which is not known at compile time if you do something like this. Okay. Alright. Oh, another thing I wanted to check in RC actually, some different implementations. Okay, impl. Oh shit. Some different. Oh my god, there's so much stuff in here. I need to scroll down. So there's implementation of. I think we need to take a look at the Giraffe implementation, right? Yeah, you implementing Giraffe. Do they even say anything? Specifically for this thing, I don't think it has to be like clonable, but it actually is. Yeah, okay, whatever. I'm already wasting time. I was just curious how if it all works. Okay, let me see. Okay, everything seems to be compiling. Now, the next thing we're gonna do, try to keep value and in this I'm already pretty safe, because if I were unsafe, my code wouldn't compile. Okay, so the new node, so begin already has something in there. All right, so it's gonna be memory Giraffe, right? It's gonna be memory Giraffe mutable, and we provide a new node, right? New node. But you keep the different values in begin and end. But how does it contradict to what I just said before your message? It doesn't. What are you arguing with? Okay, so let me see. So I'm pretty safe already, because I'm not saying a single unsafe word. So that means if my code doesn't compile, it's safe. Like, it's unsafe. So if it compiles, it's already safe. So that's my point. So I'm already safe. I don't need to be more safe. I'm already safe. The compiler actually, helps me. Alba, what's up? How are you doing? Hello, hello. We're implementing Doubly-Linked list in Rust, in a safe Rust, mind you. And we're also making a cup of tea. Programming in a weird C. I wouldn't say it's a weird C. But maybe it is. To be fair, in terms of like attitude towards programming, it's closer to C++ than C. It's safe, but it's not linked list. When you have getters, head and tail will return. How is that not a linked list? What is the criteria of linked list? I guess it depends on the definition of linked list, I suppose. What? Let's read. What is a linked list? So a linear collection of data elements. Okay, it is a linear collection whose order is not given by their physical placement in the memory. Yes, their order is not given by physical placement in memory, right? That's the whole definition, seriously, in Wikipedia. But you may argue that Wikipedia is not a reliable source of information, but it's just like, give a better definition of linked list. What? I think I could have not give a better definition to linked list than this: a linear collection of data elements whose order is not given by their physical placement in memory. That's exactly our case. So it is a linked list. It is safe, and it is a linked list. It's pointless to deny that. It's just pointless to deny that. Sorry. It's a safe linked list. Linked list deniers. We have actual linked list deniers in the chat. It's a bunch of heap allocations holding hands so no one gets lost. How does that contradict to the definition of linked list? The definition of linked list has nothing to do with allocations or anything like that. I don't understand you people. Okay. Okay, so here's a simple point, right? This thing fits the definition of linked list on Wikipedia. It fits the definition of linked list in Wikipedia. It doesn't use a single unsafe keyword, so it's a safe linked list. So that's it. So nothing you've said so far actually, you know, deconstructs my arguments. Like literally nothing you've said so far deconstructs my point. I'm sorry. Okay, let's continue. Let's continue, you know, educating ourselves. All right. You can argue about definitions how much you want. It just doesn't matter. All right. I don't know what's their problem, to be fair. I really don't understand what's their problem. I'm sorry. I'm just sitting here trying to have a good time doing recreational programming, trying to also educate myself, and some people are just trying to tell me that it's not a linked list or something. I don't know. When it's obviously is. Gatekeeping linked lists, exactly. All right, the reference. So it's going to be new pointer, right? So we just dereference this entire thing, and that gives us a mutable thing in here, right? And let me try to do that. Let me try to do that. Okay. So it means I need to set its next to the begin, right? So I'm setting the next to the begin. So next equals. So this is a node, right? So I wonder if I can do something like node. My pain, yes, it is in fact my pain. I don't remember this one. It was a huge pain in the ass. Like I remember I was trying to understand the code of my paint, and it's absolutely horrible. Like it has this weird idea of, you know, implementing core in C++, but UI in Python. It uses two different languages simultaneously. It's such a pain in the ass to build and such a pain in the ass to debug and modify. You have to jump between different languages. It was like really at a really strange era of trends when people thought it's a good idea to write UI in Python, but the logic in C++. There was like a brief period of time when it was like a huge trend, and I guess yeah. My paint is one of those programs, I suppose. Okay. So let me see what we're gonna have in here. I wonder if this will compile. So I haven't finished this entire thing. So expected pointer. Okay, so node, but got pointer. So can I just do something like this? Then, Oh, maybe I can clone it. Clone this entire thing. Then can I just clone this entire thing? Oh shit. Okay, so it seems to be working. All right. So this is going to be the next, and then I need to take the node. I need to take the begin, right? And memory deref mutable node. We might actually call it begin node. Right, this is a begin node, and its previous value is going to be actually some new node. I'm going to clone it as well. Some new node. Let's see if it's going to compile, and it does not compile. Yeah, because I renamed it to begin node. So pointer but found. Okay, so that means I have to dereference this entire thing. There was only one place. Emacs is a little bit annoying, to be fair. It just like does this thing. Expected, so I have to do these kind of things. Oh yeah, so we'll have to do it like this. So alright, where's the thing? Okay, a new node. Wait. I get really distracted too much, so I need to keep recovering my Oh, I see. I see. So that means I moved the new node in here, so I have to clone it in here. Okay. Okay, now it works. All right, all right. So that's cool, and I need to reset, I suppose, self begin to some new node clone, right? So we keep cloning this entire thing. I'm not sure why I keep cloning and why just copy won't work, but yeah. At any point, if the type system, as I already said, if the type system will become too annoying, we may strip off the entire pointer thingy and just pass around usizes, and that way we don't even have to deal with that as well. And while maintaining absolutely safe Rust, by the way. While maintaining absolutely safe Rust. So, okay, so this is just a memory allocation. In here, I need to have a memory that stores nodes of i32. And let's have something like deck of i32, right? So this is a deck of i32. And it's going to be something like that, right? It's going to be something like that. Deck push front, and let's see if we will manage to do something. We'll see if we didn't make any mistake. I feel like after this step I will just go ahead and strip off the pointers completely because I'm pretty sure I fucked up something here. We'll see about that. Might as well actually just do something like for I in 0 to 10, right, for I in 0 to 10, and just put I in here, right, and also gonna put a mutable memory. Yeah, it has to be the other way around. It has to be the other way around. All right. And it ran successfully, so now that did it run, or yeah, or we actually run it. So can I do debug print? Right, just debug print the values. I should be able to do that, so let's quickly do that. Debug print. It runs like that. Alrighty. So what we're gonna do is let mutable iter self begin while let some node equal begin. Oh, when you debug print, you actually have to pass the memory by mutable reference, right? But maybe not. Yeah, maybe not, because we don't have to modify the memory in here, so it's not needed. It is not needed. Okay. So it's gonna be something like print, and it's gonna be space memory deref. It's gonna be node. I think we'll have to dereference this entire thing. And yeah, I think that's it. Okay, so it's gonna be print ln, something like this. So it's gonna be self begin. No, it has to be iter, and then on each in this thing it's gonna be. Oh boy. So here we get the node, but we also have to take the value, right? And in here, when we dereference this thing yet again, we need to take the next value. There we go. I think that's how it's gonna go. So cannot be dereferenced. Okay, so that means I have to do like that. T cannot be formatted. Okay, so we need to also say that this thing has to be debuggable. This thing has to be debuggable. I think it's something like use std-fmt debug, right? std-fmt debug, and what do we have in here? And yeah, we also have to provide the pointer to the memory. So where's the error? Where is the error? Move occurs, so it means we have to clone this entire thing. And every time we go to the next, we also have to clone this entire thing. So I have a feeling that we'll have to get rid of the pointers whatsoever. I have a strange feeling that we're gonna get rid of the pointers whatsoever. I don't know, like implemented pointer for this thing, so it doesn't really work that well. But if I want to make this copyable, yeah, okay, I'm kind of done with it. So let's actually get rid of the pointer. So let's. I was just trying to do this as an experiment, but it's actually getting too annoying. So it does not bypass borrow checker well enough, right? It does not bypass. So let's actually put an index in here, and now it bypasses properly. So now node is going to be. Let's actually go through all this stuff. So this is going to be use size. This is going to be use size. It's just too much clone. Could not handle it. Use size. This one is more or less correct. And in here, right, by the way, so in memory, we accept this entire thing, and it has to be just use size. Bye bye, Gia. Bye bye. See you around. Bye bye. Bye bye. Good night. So when we print in something, so this is the begin, right? This is the begin. We dereference this entire thing, and let's call it node ref, right? This is a node ref, and we dereference node ref like this. Then we dereference this thing, and we don't even need to clone it because we know for a fact that it's use size, or yeah, it's a use size, right? So let's remove this clone. Yeah, let's go through the compilations, all of the compilation stuff. Oh yeah, we don't have to do that. We can just return this entire thing. Right, we can just return this entire thing. So we don't need phantom. Okay, so deck. Oh yeah, once you have deck, you probably have to put a phantom in there, right? You probably need to put a phantom into deck. Okay, so phantom data, and we're gonna say that it owns T, essentially. Right, it owns T. Phantom default. There we go. How is that not a correct linked list? This is literally a linked list. So the position of the elements is not defined by their location in the memory. So we can do push back, push front. Then if we implement like a remove, yeah, so they physically can be located anywhere within that vector, right? So their order is not defined by their like physical position in the memory. And that's literally the definition of linked list. So I don't know where people get all of these weird ideas. And by the way, it is absolutely safe. It is absolutely safe. There is not a single unsafe keyword. Like, I don't understand. It is a linked list by the Wikipedia definition. So Wikipedia gives a pretty good definition. You may say that Wikipedia is not a reliable source of information. But we're not relying on Wikipedia. We just take Wikipedia definition, we look at it and say if it's a good definition or not. I look at that definition, I think it's a good definition. It describes my experience with computer science. Yes, usually when people say a linked list, they mean that exact thing. So it's a good definition, and by that definition, our linked list is a linked list, and it's absolutely safe one. There's no single unsafe keyword. Oh. So we didn't fully implement that everything, but yeah. Okay. Let's continue implementing. So what's going to be the rest of the things? We don't have all of the operations. So it has a bunch of clones. I think we can get rid of these clones. Like, I'm pretty sure we can get rid of them. So let me try. I just want to see what the compiler will tell me, because I'm pretty sure option is copyable. Okay. Yeah, at least we have to dereference this thing. Okay, so it works like that. So quite often, well, I mean, what if I don't take this thing by a reference? That way I don't even have to dereference it. Yeah, there we go. Okay, so here's the linked list. Like, I don't understand how it is not the correct linked list. Sorry. Do not understand. Alright, so it has a couple of warnings. And all of the warnings are for the pushback. Okay, so the pushback is actually kind of similar, right? So we create a new node, we take a memory, we allocate it in here, new value, if let some end node, but this time we actually have to add it to the end, right? We have to add it to the end, so it's going to be self end, and let's put it like that. There we go. So this one is not implemented yet, but here we also need to make sure, right, that self begin is also none, right? Self begin is also none. Now, after that, we can just say self begin some new node and self end some new node. There we go. So we just added a new element in here. Cool. And here, what we're gonna do, memory deref mutable, new node. So its previous has to be equal to some end node, and memory deref mutable end node next has to be equal to new node. And after that, self end is going to be equal to some new node. So we implemented pushback, right? So now this is how push front looks like, right? This is a push front, and now if we do pushback, right? Pushback, it pushes it like that, right? So we can actually do pushback, and then starting from 10 to 20, we can do push front. All right. And as you can see, yeah, you can do push back, push front in all of one amortized because of the vector, right? Because vector push, so this is allocation. The allocation of this entire thing is all of one amortized. But you can actually make it all of one if you know upfront how many objects you're gonna have and pre-allocate the particular capacity. So yeah, it's a linked list, I suppose. You can push back and push front. We don't support actually removing elements in the middle of the thing. And what's interesting is that removing an element in the middle of a thing creates an interesting situation. Basically, it fragments the memory of the allocator, right? So if you remove something from there, you basically lose the object, and that object becomes inaccessible because we're allocating at the end. We push back to the end, so it actually kind of like wastes a little bit of memory. And what I'm thinking is that maybe we could introduce deallocation. So what if we could say that, okay, I'm done with this object, please deallocate an object at that particular index. You know what I mean? So then you can reuse this object. You know what I mean? So, but to be fair, how can you reuse it? We can mark some of these elements to be free, right? We can mark them to be free, but then allocating is going to be actually O of n, which is very slow, right? You have to go from left to right and look for those things. I have a better idea, actually. What if you deallocate an element, we're going to push it into like free here. Right, so every time you deallocate this thing, what do? We do self free push pointer, like this. And now, when you're trying to allocate something, we're first gonna look at free and see if we have any free slots. And we're gonna allocate that thing there. If we don't have any free slots, we're gonna push a new thing in here in buffer. And that way, you have dialog, O of 1 amortized, and alloc still O of 1 amortized. So, but now you can reuse the memory at least. Is that a good idea? What do you guys think? Is that an interesting idea? I think it's actually a pretty interesting idea. So we're essentially like implementing our own allocator, essentially based on vectors. And essentially, deck, when you remove an element, right? When you remove a particular element, it will also have to deallocate the corresponding nodes. So adding n elements and removing them leaves you with O of n memory consumption. Yeah, essentially, just like in case of a vector, right? Because it also maintains a certain capacity, right? So essentially, if you push n elements to the vector, to the Rust vector, and then clean it, if I understand correctly, at least majority of the vector implementations do it like that, it will still leave the n memory consumption. So just like any data structure. So it's actually a pretty common thing to do, isn't it? C++ vectors do the same thing. A lot of dynamic array implementations in C do the same thing, right? So then later you can actually push faster. You can push with O of 1 without reallocating anything. So is that something bad in your opinion? I don't think it's something bad, considering that in 2021 the memory is cheap. So can you still read from index which is also in free though? Yes, you can. You can actually even accidentally read from a wrong index and corrupt the memory. And that is 100% safe Rust, because I'm not using any unsafe keyword, and Rust doesn't complain. So corrupting memory is absolutely safe in Rust. So I can just read the wrong index. The compiler won't tell me anything. I didn't use any unsafe features. It is totally fine. This is safe Rust. It is absolutely safe. You want to argue with that? I don't know how you're going to argue with that. It's safe. I don't use a single unsafe keyword. I don't know what you guys are talking about, but it's absolutely safe. So, to be fair, it is safer than row pointers because at least you have like a boundary checks from vectors and stuff like that. So you also, even if you go like out of buffer, usually the data that is stored there is not executable, right? So it's already more safe than just row pointers in C. So yeah. In all fairness, it is still safe than C, right? Because again, in C there's no boundary checks. You at least have boundary checks in here. And also this memory is not executable. Sometimes in C, depending on how a compiler will compile that, and also depending on the runtime, you would be able to corrupt executable memory and actually do arbitrary allocation. So in all fairness, it's a little bit more safe than C. Just like any language that came after C. Anyway, well, not really, not really true. Not really true. There's also C++ that came after C. Okay. So what we're gonna do in here, so I implemented the allocation, right? So we need to come up with an interface for, so self missing 3, okay. So it's gonna be, I think I can just do something like this. I think I can just do something like this. Yep, seems to be working. So how are we going to be deleting the indices? How are we going to be deleting the indices? So we do have the pointers to certain, yeah, so the pointers to the nodes are stored in here. So essentially, what we can do, we can implement something like fn delete, right? And it's going to be immutable self. It's also going to accept immutable memory. It's accepting immutable memory. And also an index inside of that memory of the node that you need to remove from the DAC. All right, so so the first thing we need to do, and of course you can actually put absolutely incorrect index in here and remove something that does not exist in a DAC at all, and that's going to be totally fine. That is totally safe because I don't use a single unsafe keyword, right? If it was unsafe, Rust would tell me something, at least. So now what I'm going to be doing here, oh yeah, let me see. So we are about to remove some stuff in here. All right, this usually goes like this. All right, so you need to take a look at the previous one, and sometimes, to be fair, I think you have to be a little bit more careful with this kind of thing. Because you need to check if you point at the begin or you point at the end, right? So you need to check if you point at the begin, because then you'll have to update the begin and end of the DAC, right? So for now, let's actually implement something like pop back and pop front, right? So pop back is going to be immutable self. You will have to accept immutable memory, right? You have to accept immutable memory, node T, and something like this. So what we can do in here, we can assert, right? We can assert that self and is sum. So it has at least something, right? It has at least something. So after that, what we need to do, we need to save the end, right? Well, you know what? We can actually do it a little bit differently. So if let some end node, maybe end ref, self end, right? Otherwise, we're just not going to return anything. So here's the reference, right? Here's the reference, and one of the things I want to do, I want to save it to delete, right? So to delete, or maybe let's call it to dialog. To dialog and ref. So you'll need to deallocate this thing a little bit later. Well, since we're copying it, so it shouldn't be that difficult. Okay, so then self end should be equal memory diref and reference. So it's an end reference. We then take previous value from it. We take the previous value from it, and we assign it back to the end. Because of that, we're sort of losing end reference, but we don't actually lose it, to be fair. We don't actually lose it. We can put it here, and then we can say memory, deallocate, and reference. You can hear my neighbors? I really apologize for that. I really apologize for that. Okay, so this is how we can do pullback. Alright, this is how we can do pullback. So we take the end, if it has something, we dereference that end, and we move to the previous value, and then we deallocate that value from the memory, so next time you push, you can reuse that value, right? So we are reusing these elements. And I really apologize for my neighbors. I really apologize for them. So it will be kind of cool to at least inspect the memory and see what's there. Yeah, so we have debug print. Okay. So maybe we can implement something for the memory as well. Maybe we can implement something for the memory as well. And we can also do pop front as well. Pop front, mute self memory, mute memory node t, right, node t, if let's some begin reference, right, begin reference self and, okay. So self begin is going to be equal to memory deref, begin reference is going to be next, and then you have to not forget to deallocate at that begin reference, otherwise you're like leaking memory. And we don't want to leak the memory because it's 1970. We cannot just let it leak. The memory is expensive, okay? The memory is in fact expensive. You cannot just let it leak, am I right? Right, so let me see what we got in here. Okay, so we have that deck, something tokens. Ah, I see. What are you guys talking about? Oh, dialog. Yeah. All right, cool. But it's still absolutely safe, as you can see. So the we don't use a single unsafe keyword, so it's totally fine. Right. So what I want to do actually here, I want to just print the deck, and after that, I want to try something like for I in 0, 10, we're gonna deck pop front. Right, that's gonna be deck pop front. It's gonna be deck pop front, and yeah. So we have that, and then we pushed more things, and maybe I can actually do something like 20, and it's supposed to actually remove all of them. So as you can see, it removed all of them. Maybe it would make sense to surround them with something like this, right? Yeah, you can clearly see how it works. So another thing I would like to do, I would like to just dump the memory. I think for the memory it should be enough to have something like derive show. I was listening to the stream in the background and my Russian ass thought you were saying dialogue when you were actually saying dialogue. I see. Right. When I was young, Nibble was enough. Is that like 4 bits? I think it's 4 bits. Okay, show. What the fuck is... What show? Fucking... Okay, debug. That's what I wanted to do. Alright, so after each allocation, what I want to do, let's try to take the memory, right, and just print it with the debug, right. Just print it with the debug, and let's see what's gonna happen. Let's see what's gonna happen. Okay, so it didn't properly print anything. Cannot be formatted with node. Node has to be also debuggable. Okay, so let's actually make a debuggable thing. Oh, that's a lot of shit. Maybe we could reduce the scale, or maybe just implement it a little bit nicer. So let's not use this shit. Let's implement our own thingy. I'm sorry if it was too loud. I just hit the mic. I didn't expect to hit the mic. I'm sorry if it was too loud. So let's do debug print, and it's gonna be self. All right, so it's gonna be like not really loud. Okay, thank you. Was it loud or was it not? So iGooduk says it was not loud. Deep Singularity says it was loud. I'm really sorry, Deep Singularity. I didn't mean to make it loud. It just was completely accidental. So self. It was for me. I'm really sorry. Sometimes I just do a lot of hand waving, and sometimes I hit it. I didn't mean to. Please forgive me. I'm so sorry. So it's gonna be buffer. I'm so sorry. Please. I have to be really careful. Like sometimes I just forget that. Yeah. Oh, God. And yeah, we lost actually viewers after that. So, some people just silently left the stream. So. Okay, so this is gonna be free, and then we'll have to do something like free. So what does it say in here? X, yeah, we have to do something like this thing. Okay, so and this thing is not debuggable, right? So we have to actually make sure that it is debuggable. What do you want from me? Node debug. Okay, so node also have to be debuggable. Sure. What else do you want from me? Cannot be formatting because debug is not implemented for. Oh yeah. Okay, so now I can just do debug print. Okay. It's so goddamn fucking annoying. Holy shit. So can it move? It's the most annoying language I've ever programmed in. Holy fucking shit. Alright. And it still doesn't. Okay, maybe instead of nodes we could print. I don't care, to be fair, too much about the information in here, right? I just want to say, I just want to indicate that these things are taken. And it's been so much time, nobody remembers what I'm doing and why I'm doing all of that, so I have to remember it from scratch yet again. It's so fucking annoying. Oh my god. Yeah, it's gonna be print ln. Does anyone know what I'm doing right now and why I'm doing this thing? Probably not. I have to explain it yet again. Alright, so essentially this is the state of the allocator. This is how many cells we allocated in the buffer. And this is the free cells. This is the free cells. Right, you see, after the first iteration, when we pushed first 10 element, we pre-allocated 10 elements in here. Right, so then we pushed another 10 elements in here, and there you go, here is another 10 elements. And then we freed 20 elements, and now here you go, you have 20 elements in here. So here's an interesting thing, we can try to push another 10 elements again, and according to my calculation, that shouldn't grow the size of the buffer, but it should shrink the amount of like free cells that we have, because it should take them from the back. But I think it won't do that because we haven't implemented that yet. I think. Yeah, we haven't implemented that yet. Yeah. So this is precisely what we need to implement. So, and this is precisely why I was implementing this routine, so we can see what's going on inside of the memory allocator. All right, so let me see. So when you deallocate, yeah, when you allocate something, first you need to check if you have something in free. So you have to go self free length. If it's greater than 0, right, if it's greater than 0, we're gonna actually simply self free pop. I wonder if you can just pop out of the vector. Is it safe? Yes, it is absolutely safe implementation. If it was unsafe, the Rust wouldn't let me to compile that because I don't use a single unsafe keyword. I don't use a single unsafe keyword. It's absolutely safe. All right, so can I just try the following thing? I think I should be able to do something like pop. Pop. All right. So, and this is going to be something like x. And we simply can return x. Actually, yeah, let's call it index. Right, and we'll have to do the following thing: buffer, add that index equal value. That's the first thing we do, and we just return an index. Otherwise, we push a new value, and we just do it like that. Okay. So now we are reusing the freed memory. We are reusing the freed memory. Okay. As you can see, after that, the amount of free cells reduced, right? And the size of the buffer didn't grow. The size of the buffer didn't grow. That means we are reusing things. Like after that, we can even try to print the deck as well, just to ensure that it contains correct data. Just to ensure that it contains correct data. So it's going to be debug print, and there we go. Yes. I forgot, what is it called? The debug? Oh yeah, you have to provide the memory. It cannot leave without the memory. Okay, so it's going to be something like this. And it contains nothing. Oh, that's very interesting. So we have a bug somewhere in implementation. So let me see what we have in here. So begin has to go to next. So, well, I just pushed into the deck and it doesn't contain anything. So Let's do that after each of them, right? Let's do that after each of them and see how they go, right? All right. So after that one we have this, after that one we have this, after that one this is free, and pushing again didn't push anything new, so something went wrong. It's a bit weird that for every free slot we actually have to spend 8 more bytes to store the index. I mean, memory is cheap, so the end previous. Push element. So when we're allocating this entire thing, we're moving that value there. To be fair, I'm not sure what the fuck is going on and why it is not updating properly, but maybe I need to make a small break because I'm already tired of like doing that for 2 hours already. I probably missed something. Probably missed something obvious. So one of the things I probably want to check, is the begin and end of the deck and just see if it's like none. I could probably, maybe for the deck, yeah. So after we popped everything from the deck, we're printing that deck, and I want to print ln begin. It's gonna be deck begin, and it's gonna be end. Cannot be formatted. Okay, so we can probably debug it. We could probably debug it. Yes. I made a classical mistake. Alright, so some of the end actually was left unfinished. Okay. Interestingly, yeah. So how do we detect that? I suppose if after all of that end is none, right? If self end is none, I have to set self begin to none as well. Is that a reasonable thing to do in here? I think it is. And this has to be a function. This is going to be end. And now it works. Okay, so it was a bug in implementation of these things. Right, so as you can see, we are reusing the elements. Right, we are reusing the elements. So memory debug print. Okay, cool. But do we actually wait? Oh yeah. Okay. I wanted to remove this thing. So, and I want to try to push front more elements and see if it's going to be the same amount of memory usage. Yeah, there we go. So still the memory doesn't grow. We're actually reusing the memory. And as you can see, the order of these elements does not depend on their order in physical memory. It depends on their pointers to the next in previous. It is a correct linked list, whether you want it or not. According to that definition, it is a correct linked list, and on top of that, it is very safe, right, because we don't use a single unsafe keyword. All right, so So what I want to do in here is probably maybe print this entire thing here like that. What if you push more, you have free? Will it use both free and unfree? If you push more, then you have free. It will extend the buffer. So for example, here we pushed more than we have free. At the beginning we have 0 free and 0 allocated. So there you go. It just keeps allocating these things. But then as you deallocate, it starts marking, okay, the thing at that index is free, the thing is at that index is free. Okay, let me demonstrate. That's what happens. You see? So we used up all of the free, so we extended the buffer even longer. And if we deallocate all of them, all of these indices will go into the free that can be reused. So yeah, yes. That's how it works. Also, let me put it like this. And the thing I want to put in here, I suppose I want to do print ln. Yep, something like this. So I want to actually, to be fair, how I want to do that. So at the end of these things, I might just do a double equals. It's kind of difficult to provide any useful thing in here, but I tried. Maybe it would make sense to not separate these things at all. I just want this thing to make sense somehow. All right. And for maybe for that one. Empty lines, maybe. Okay. So we have a so it's slightly different order. Okay, so I guess I'm done with today's implementation. I think it's pretty cool. We implemented our own allocator. I never implemented my own allocator that actually reuses the memory, to be fair. This is my first time. Usually the allocators that I implemented were just linear allocators that clean everything at once. All right, I never implemented that allocator that just deallocates specific objects and lets you reuse the specific objects. So yeah, that was actually pretty cool. I learned a lot of things. So what do you guys think? What do you guys think? Is that was it educational? Was it interesting? We also learned how to bypass the Rust borrow checker. So I think I demonstrated quite well. So every time you have any problems with borrow checker, you can just easily bypass it with indices. Right, just use indices instead of references. Pointers is just like it, quite easy. And all of the guarantees and checks are going to be lifted without you using any unsafe. It is totally safe. It is a totally legit way of bypassing borrow checker, and you can use it. Everyone can use it, and that's why I'm sharing it with you, so you can use it too. So as you can see, not a single unsafe keyword. It's absolutely safe. Corrupt memory. Because it depends on the definition of corruption. It makes it kind of easy to alias memory and stuff like that. So yeah, it's pretty cool. It's pretty cool. So there is an official way to bypass the borrow checker. Nice. Will I write a book about this? I don't know. I think a lot of people already did write. I don't know. I don't think I'm adding anything new to the conversation. So it was. I do realize that. Okay, so probably people who invented the entire borrow checker system, I don't think they're dumb. I'm pretty sure they're pretty smart. They're pretty smart people, and they know about this, you know, backdoor to the borrow checker. And as far as I know, this backdoor is quite heavily used in the compiler itself. So I'm pretty sure the entire borrow checker system is not about that. So essentially, it's just like saying I know what I'm doing. It's like another way of saying I know what I'm doing to the compiler, right? So yeah, just another way of saying you know what I'm doing. My goal was just to debate people who tell me that this is not the correct linked list. That was my goal today. So I'm not saying that Rust is bad or like Rust people hypocritical. It's just like I'm pretty sure they're pretty smart people. They all know all of that. I'm not, you know, reinventing the wheel or discovering something that everybody fucking knows that. I was just wanting to debate people who will tell me that it's unsafe or it is not correct list or something like that. Some bullshit like that. Holy shit. So that was my whole goal, nothing else. That was my whole goal. Just to debate some people. All right. Implement deck based on doubly-linked list, and I really recommend you not to take me seriously, right? So as just like I'm doing that for educational and recreational purposes, right? So I think this kind of exercises help you understand the language a little bit better, and also we implemented an allocator that also, you know, returns the memory. Okay. So you can find the source code in here if you're interested in this kind of stuff. You can find the source code in here. All right, and I guess I gotta go. It was fun. It was fun. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you all tomorrow. Tomorrow we're gonna do something I don't remember. I think we're gonna be working on our language. Check out everything, check out the project, check out the schedule, check out the VODs, check out the channel and all of that stuff, and I see you all. Not channel, but I mean Discord. I think I went to put Discord. Alright. Thanks everyone for watching. Love you. Mwah.